One of the foundations to cybersecurity is detection. We need to be able to detect cybersecurity events to be able to respond and recover from them effectively. Many times attackers can be in our networks for weeks, months, or even years before they're detected. One of the challenges is that once they're in an IT network, they use tactics and techniques that appear to be legitimate. They might use things like valid credentials or remote access to be able to access the control systems. A lot of times the attacks also don't utilize malware. They might change set points or logic configurations, and these can be very difficult to detect. So we've been looking into ways to utilize machine learning and digital twins to detect anomalies to the operating systems as an indicator of a cybersecurity event.
This project provides an exciting new take on applying relatively inexpensive IoT sensors and use supervised learning with a digital twin approach to independently provide equipment monitoring capabilities and identify changes in operation which may be tied to cyber attacks. The approach used in this was to intake data for inexpensive sensors doing an EPRI flow loop operation and to feed this data into a digital twin model to apply machine learning algorithms and to identify potential anomalies affecting system operation. This disruptive technology approach can be potentially operated independently in a secure wireless platform, and it may provide a low-power solution that can be applied to various plant assets, especially where limited access and costs prohibits traditional monitoring. In addition to system operation anomalies, the process can potentially detect network intrusion and/or tampering of operation parameters that may not be immediately picked up by plant operators.
This project builds on our existing research that was funded by the National Science Foundation with Washington University, where we did combustion optimization. And basically, we realized that the same digital twin underpinning could be used to detect anomalous behaviors and potential cyber attacks in these same systems. We were able to compare various different models, and we found that out of all the different models, certain ones performed extremely well beyond our expectations, up to 99.9% accuracy. We were able to flag operational anomalies like pump cavitation or operator errors. And interestingly, what we were able to find is that we were able to see what type of anomaly it was because the models performed so accurately. So with these results, the staff would be able to investigate potential cyber attacks or other anomalies before they could do any real damage and have lasting impact.
The proof of concept results were very promising. We were able to deploy low-cost sensors quickly and easily in the lab environment. By doing this, we were able to detect operating anomalies to some of the equipment that we had in the lab. These could be indicative of a cybersecurity event, but they also could be indicative of other things as well. We were able to, with this limited data set, start with that classification process, but we do need to work with members to generate and gather more data and look at different types of events as well. We're also optimistic that by correlating some of this operating information to security alerts and network traffic, we can provide a very high level of detection capability for some of these attacks that are very difficult to detect.